Okay, we're about to blast through a ton of information, so I'm probably going to go quickly through this. However, I will review it once we're in class. What is an orbital? We've been talking about orbitals, and we've also mentioned Heisenberg's uncertainty principle, which says that there's no way to exactly say where an electron is located. It's more of a probability. An orbital is a graphic representation of the space that an electron will occupy 95% of the time. It's a concept, not a physical structure. So this area right here is where the first two electrons will be 100% of the time. 95% of the time, they'll be in this area. So we call this the 1s orbital. Okay? And it's just a graphic representation. It's not like a shape. Electrons are added to the lowest energy orbital first. That's called Aufbau's principle. It's because nature always favors lower energy systems. Alright, and then you guys know this whole thing right here. There's 4 different sublevels. The S sublevel, the P sublevel, the D sublevel, and the F sublevel. Notice that the 4 different sublevels always start with that number. The first sublevel starts with the number 1. That's the principal quantum number. The second sublevel starts with the number 2. The third sublevel starts with the number 3. And the fourth sublevel starts with the number 4. Okay? Only 2 electrons can fit in the S sublevel, 6 in the P, 10 in the D, and 14 in the Fs. And we're going to go through this more in class. So hydrogen has 1 electron, therefore we put it in the 1s orbital. So its electron configuration 1s1. Helium 1s2. Lithium 1s2. Now it's filled up. You enter the next energy level 2s1. Beryllium 2s2, etc., etc., etc. Remember that the shortcut is you can say the noble gas before it and then start from the next energy level. So oxygen, instead of 1s2, 2s2, 2p4, it's just helium, 2s2, 2p4. Down here at sodium, instead of 1s2, 2s2, 2p6, 3s1, we say right here, this is neon, 3s1. Okay? All right. If you're filling in orbitals, orbital diagrams, remember we use arrows to represent the electrons, one pointing up, one pointing down. This represents the spin, clockwise, counterclockwise. Okay? There's a couple rules. Always enter lowest energy first. Then we're going to put no more than 2 electrons per orbital. 3 is a crowd. And then we're going to put 1 in each before we double up for degenerate orbitals. I'll mention that in just a second. Aufbau rule is that you put it in the lowest energy first. Pauli exclusions principle says only 2 electrons per orbital. Hund's rule says 1 in each before you double up. Here's lithium. Okay, here's fluorine. Notice we went 1 up, 1 up, 1 up before we started going 1 down, 1 down, 1 down. Okay. Nitrogen has 3 electrons in the 2p sublevel. You do not go 1 up, 1 down, 1 up. It's more like filling in seats on a school bus. You put 1 in each before you start doubling up. Place 1 unpaired electron in each degenerate. That means same. These all have the same energy, so you put 1 in each. These orbitals have all the same energy. Orbital that all spin in the same direction before adding electrons that spin in the opposite directions. Okay, carbon looks like this, 1s2, 2s2, 2p2. You've got 1 up, 1 up. Lone atoms with 1 or more unpaired, these are unpaired electrons, are attracted by a magnetic field, and we call them paramagnetic. Lone atoms with no unpaired electrons, like neon, neon is 2p6, all the electrons are paired up, repel magnetic fields, and therefore we call them diamagnetic. Okay, we're going to go into periodicity. I'm going to go a little fast with this. There's a bunch of trends that we're going to start talking about: atomic radii, ionic radii, ionization energy, electron affinities, and electronegativity. Okay, atomic radius, if you'll remember, increases going this way and down. Why does it increase going down a group? There's more electrons, there's new shells added, so it gets larger and larger. Why does it increase going from left to right? Well, the valence electrons are all in the same shell still, okay, and they have the same energy. Moving from left to right, you're adding more protons. As you're adding more protons, this increases the force of attraction experienced by the electrons, thereby decreasing the radius. It has a stronger effective nuclear pull on those outer electrons. Ions. I've got cations and anions. Remember, cations are positive. Why? Because they lose an electron. Nonmetals tend to gain electrons. Those are called anions. Metals are here, nonmetals are there. Okay? All of these right here are called isoelectronic. What does that mean? They all have the same electron configuration. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. Chloride is 3s2, 3p5, but since it's -1, you added another electron, so it's 3p6. Sulfur is normally 3s2, 3p4. You added 2 electrons, so it's 3p6. Calcium is usually 3s2, 3p6, 4s2, but you lost 2 electrons, 3p6. Potassium is usually 4s1, lost 1 electron, 3p6. They're all isoelectronic. However, as the ratio of protons to electrons increases, the force of attraction also increases, and therefore they get smaller. So for example, here's potassium, just regular potassium right here. But potassium plus 1 loses an electron. Now my number of protons to my number of electrons has increased, therefore it tightens up and gets smaller. On the other hand, here's chlorine, here's chloride. If I add another negative electron right here, okay, if I'm adding a negative, what's going to happen to all those other negatives? They're going to repel and it's going to get larger. So anions get larger, cations get smaller. So ionic radius, what happens? Well, if you go down a group, you're still increasing your number of shells, so it just gets bigger. But if you're going from left to right across a period on the periodic table, the radii of the cations, positive ions, decreases as the effective nuclear charge is increasing. Okay? But when you encounter your first anion, remember the anions are going to be bigger, so there's going to be this dramatically increase in radius. But as you continue on, they're going to get smaller and smaller and smaller. Ionization energy is the amount of energy needed to remove an electron from a gaseous atom that's in its ground state. Energy must always be added to remove an electron. Okay, you have to replace that electron with some energy. It increases going this way and up. Why does it increase going up? Well, the electrons are closer to the nucleus and therefore more difficult to remove. Why does it increase as we go this way across the periods? They have more protons as we go this way. The larger the number of protons, the stronger the effective nuclear pull on those outer electrons. Here's a graphic representation of ionization energies. Notice that the noble gases all have the highest ionization energy because they have filled sublevels, therefore they are not going to remove an electron very easily. And as we go down, those electrons are further away from the nucleus, therefore easier to remove. Generally, increase in atomic radius decreases ionization energy, okay, due to the stronger force of attraction between protons and valence electrons. It requires more energy to pull an electron from a full D sublevel than it does to remove one from a P sublevel. It requires more energy to pull an electron from a full S sublevel than to remove one electron from a P sublevel. That single electron is easier to remove as it's only in an electron of a higher energy level. The second ionization energy, that would be the energy needed to remove a second electron, is always greater than the first. Why? Because the radius is reduced after the first electron is removed, and the ratio of protons, positive charges, to electrons increases, therefore making it more difficult to remove another electron. However, every element has a huge dramatic increase in one ionization energy. This occurs when the electron configuration drops a principal quantum number, causing the radius to shrink much more than other ionizations. I'll show you this in class. Electron affinity is the energy change that occurs when an electron is added, not removed, added to an atom to form a negative ion. It's a measure of how much an element wants to accept another electron, but remember, we don't use terms of wanting and desire. If the value is negative, it releases energy. Okay? It wants to accept an electron. The more negative, the more it wants to accept it. If the value is positive, it requires energy for you to give an electron to it. It does not want an electron. For example, if I have a filled S sublevel, okay, you're not going to be giving this guy right here another electron. It does not, quote unquote, want one. Noble gases, likewise. You're not going to be able to give the noble gases an electron. They don't want one. Okay? All these other guys here, they need some electrons. Okay? Halogens, they want another electron to become like the noble gases. So electron affinity increases going this way and up. Electronegativity is the element's actual ability to attract electrons in a chemical bond. The electrons will spend more time around the more electronegative element. That increases going this way and up, except for the noble gases, because obviously they don't tend to attract electrons.